Hi everyone. Today we're going to talk about the two important ideas in programming called abstraction and encapsulation. These are part of something called object-oriented programming or OOP. Now let's dive in OOP. Let's understand first what is OOP mean. OOP it's a way of writing code that is organized around objects just like a real life. Think of a dog. A dog has information, its name, breed, and age, and it has actions. It can bark, run, and eat. In OOP, we represent the dog as an object with data and behavior. OOP has four main ideas: abstractions, encapsulation, inheritance, and polymorphism. Today, we focus on the first two. Abstractions means hiding the complicated parts and only showing what's needed. Encapsulation means keeping data safe by wrapping it inside protective shell. Now, before we dig deeper, let's first understand the history of OOP. To appreciate where OOP stands today, it helps to see where it came from. It all started in year 1960 with Simula 67 created by Oli Johan Dahl and Christine Yagard. This was the first language to introduce the concept of classes and objects. Revolutionary at the time. In year 1972, Alan Kay at Xerox PARC coined the very term object-oriented programming and developed Smalltalk, a language that pioneered encapsulation as a core design philosophy. Then came in the year 1980s C++, where Jan Strostrup extended the C language with OOP features, bringing the paradigm into system programming for the first time. By year 1995, Java and Python emerged, bringing OOP to the mainstream software development with strong abstractions models that developers still rely on today. And from 2000 onward, OOP became truly universal, foundational in C#, Ruby, Swift, Kotlin, and even virtually every major modern language. Now, let's understand what is the importance of OOP in software engineering. So why does this matter for software engineers? Let's look at 6 key reasons. First, we have the complexity. Why? Because abstraction reduces cognitive load. Instead of worrying about every low-level details, engineers can focus on high-level design. And also, it helps in data security. Why? Because encapsulation protects an object's internal state from unintended modification by enforcing access through getters and setters. We maintain data integrity throughout the system and also help in code reusability. And the encapsulated modules can be dropped into multiple projects without ever exposing their internals. That dramatically reduces development time. And also, it is important in maintainability. Why? Because changes inside the class don't break external code as long as the interface stays consistent. This is used in the large-scale system where the teams can't afford cascading failure. And also important in team collaboration because abstraction lets different teams work on different modules. Why? Because as long as the interfaces and contracts are clearly defined, teams don't need to know each other implementation details. And lastly, it is important in scalability because the encapsulated components are independently testable. and deployable, which is exactly what microservices and modular architecture at scale require. And what is the applications of OOP in software engineering? So these principles are not just academic. They're used everywhere in professional software development. Let's walk through some real-world examples. So for example, in abstraction side, it apply in interfaces. When you call a REST API, you interact with the endpoint. You don't need to know anything about the server logic behind it. And also in Java abstract classes, it defines the blueprint that subclasses must implement, enforcing consistent behavior pattern across the system. Database layers, ORM frameworks like Hibernate let developers interact with databases through objects method, abstracting away the raw SQL entirely. And also it can be applied in GUI toolkits. UI frameworks let developer describe what to show, not how pixels are rendered on the screen. On the encapsulation side, it uses in-access modifiers. Private and protected fields in Java, Python, and C# are the most direct form of encapsulation, restricting what outside code can touch. And also can be applied in banking system. For example, account balances are never modified directly. Transactions must go through validate methods, ensuring rules and constraints are always enforced. And also can be applied in healthcare software. Patient records are encapsulated to enforce HIPAA compliance and prevent unauthorized access or modification. And also can be applied in game development. Player status and scores are managed through methods that enforce game rules. You can't just set your health to a maximum level from outside the class. Now, for the conclusion of this presentation, let's bring it all together. So we have the abstraction is essential because it allows engineers to manage large complex code bases without being overwhelmed. It enables scalable, maintainable system design by letting us operate at the right level of detail. And also, encapsulations protects integrity. It enforces the single responsibility principles and prevents unintended state changes, which is especially critical in high-stakes domains like enterprises, healthcare, and finance. Together, these principles are foundational to modern development. From mobile apps to cloud-based microservices, abstractions and encapsulation show up in every major programming languages and design frameworks in use today. And despite of decades of evolution in software engineering, they remain as relevant as ever. And thank you for listening to my presentation, and here is my slide, my references. Okay, thank you and goodbye.